Kajala Medical presents COVID-19 The Answers, the show that delivers the scientific, evidence-based knowledge that can safely return us all to our pre-COVID lives. My name is Dr. Fumi Okunola, and I'll be hosting the show. Every week, you can listen to me interview a highly respected professional about the science that can reduce your risk of becoming infected with this coronavirus. Hello and welcome to COVID-19 The Answers, episode 12, FAR UVC. I'd like to welcome Professor Kirk Atkinson, PhD. Professor Atkinson is an Associate Professor and Associate Industrial Research Chair of Energy Systems and Nuclear Science at Ontario Tech University in Canada. Dr. Atkinson graduated from the University of London with a BSc in Theoretical Physics in 1999, an MSc in Astrophysics in 2001, and an MRes in Image and X-ray Physics in 2002. He then joined the Ministry of Defence as Senior Lecturer in Nuclear Science in the Nuclear Department, the UK's only dedicated nuclear engineering school. He became Technical Lead for Reactor Physics and High Performance Computing, and for Radiation Physics and Criticality. Since 2014, in collaboration with Rolls-Royce, he led a multi-million-dollar technical effort to develop a high-throughput gamma-emission tomography system for imaging and characterization of spent nuclear fuel. He joined the Faculty of Energy Systems and Nuclear Science at Ontario Tech University as an Associate Professor in January 2019 and began collaborating with research into FAR UVC with Professor David Brenner's team at Columbia University. Welcome.
Hi.
So Kirk, could you tell the audience what led you into the world of FAR UVC technology?
Yeah, I had a background from my PhD work in radiation biology, and I found myself a little bit stuck moving my family funnily enough, from the UK to Canada, and I was trying to leverage my skills and experience with that background and my background in nuclear engineering and modeling and simulation. And I sort of stumbled across the work that David Brenner had been doing, who I knew from before, at Columbia University. And I noticed that whilst they were doing some really good stuff in the experimental side, the widespread application, how it would work in practice, in the environment, in a building, wasn't really well worked out at all. So they'd concentrated much more on the laboratory studies and the science of how it does the killing rather than how it would work in practice. And so with some colleagues from the UK, we decided to do some simulation work to try and figure this kind of thing out. And it's been quite influential, I think, in terms of the findings that we've found, and we've actually been able to help the Brenner Group interpret some of their work, and actually found that FAR UVC is even better than we thought it was going to be.
Oh, that's fantastic. So electromagnetic radiation is a term used to describe all the different kinds of energies released into space by stars such as the sun. The energy travels at the speed of light and is in the form of waves and photons. When you wake up and see the light from the sun, tune your radio, watch TV, send a text message, or warm food in a microwave oven, you are using electromagnetic energy. You depend on this energy every hour of every day. Without it, the world you know could not exist. In the electromagnetic spectrum, there are all types of electromagnetic radiation with various frequencies and wavelengths. The most well-known are radio waves, microwaves, infrared, visible light, ultraviolet, and X-rays. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. Today we will be discussing ultraviolet light, or UV light, and FAR UVC light in particular, as it relates to the preventative measures for COVID. This technology is widely unknown, and safety of use will be a major concern to educate medical and non-medical people. UV light has different properties and uses in industry and everyday life, as well as pandemic management and risk mitigation. So, Kirk, before we dive into this technology and its application for COVID risk mitigation, let's begin with a very basic understanding of the technology. Can you briefly describe the three different types of UV light and their uses, UVA, B, and C?
Sure. So UV light exists at shorter wavelengths than visible light. So most of us, maybe in school, did a little bit of physics, and somewhere along the line, the acronym Richard of York gave battle in vain, or Roy G. Biv came up. And so you're going all the way from the red, the R, to the V, the violet. The violet is around about 400 nanometers. When you go a little bit to shorter wavelength from there, yeah, so below 400, maybe to as low as 315 nanometers, that's in the ultraviolet range, and that's the ultraviolet A range. So that's what we call UVA. And that's the wavelength of light that we're familiar with. It's what causes people to tan when they go in the sun. It's what causes skin to age if you don't, moisturize and take care of your skin properly. It's what you use in a bug zapper. Yeah. Now, if you go to shorter wavelengths, go a little bit shorter, we hit the UVB range. Yeah. So that's between about 315 nanometers and 280 nanometers. And that's maybe less useful in some regards. It can be responsible for causing melanoma in terms of skin cancer. It's one of the ones that we know about a lot. So one of the reasons we should wear sunblock when we're in the sun or protect ourselves. But it causes fluorescence. Yeah, so you can use it in fluorescent applications. Go a little bit shorter wavelength still, below 280 nanometers, and you enter the UVC range. Now that UVC range pretty much exists between about 200 and 280 nanometers. There are bands of UV light that exist at shorter wavelengths than that. Yeah, what we would call the VUV and the EUV range, and they have specific properties as well. But if we focus on that 280 nanometers down to 200 nanometers range, yeah, where we have UVC, the most common kind of wavelength that we know about is around about 254 nanometers. And that's used in sterilization purposes. When we go towards the very short wavelength end, that's where we hit what we call far UVC. It's at the far end of the UVC range. Yeah, it's always existed, and it's really within the range 230 nanometers down to about 200, with the common ones being between 222 and 207 nanometers. And that's really been an underutilized wavelength range.
Right. And just to clarify for the non-scientific audience, so UVB, when you talk about fluorescence, you mean in lighting. So, for example, nightclub lighting, and that blue lighting you see that we sometimes see in shops that kills bugs. That's what UVB is used for.
That's not what UVB is used for. The fluorescence, I mean, in the sense here, is more to do with particular kinds of scientific applications. You can get fluorescence at all different kind of wavelengths, whether it's UVA through to X-ray through to whatever. All fluorescence really is the light that becomes emitted through the excitation of electrons in an atom. So if you go back to school now, many of us would have probably done chemistry class, maybe physics class, and they would have remembered that the atom is kind of like has a blob in the middle. That's the nucleus, where we've got some protons and stuff going on, and then orbiting around that. And the important word here is orbiting, are electrons, and those electrons can live in different shells. So when we cause an electron to be promoted from a lower shell to a higher shell, it doesn't necessarily like to live at that higher shell state. So what it does is it relaxes back down and gives off light in the process. And that's fluorescence.
Right. Okay. And then UVC, when you said it's used in kind of sterilizing properties. That's
Yep.
practically speaking, that's things like our operating theatres. They use UVC, at night, don't they, to sterilize them when nobody's around. So that's one of its uses too. Is that right?
Yeah, so UVC more recently has been used. So traditional UVC more recently has been used in the operating room, emergency room kind of context, out of hours. But for the longest time, it's been used in other contexts too. Many of us here in Canada and in maybe in the US and other places might take water from a well, or has fairly unclean water from in the mains, and so they want to sterilize it. Now you can go down to many hardware stores, certainly here in Canada, and you can buy UV apparatus that will illuminate the water and kill the bugs that are in it. You can put the same kind of thing into HVAC systems. So the idea that it's been used for germicidal purposes to kill germs has actually been around for about 100 years. And it's really, really well established.
Thank you. And yes, and Professor Jimenez talked about it a couple of weeks ago, germicidal UV. What's the difference between conventional germicidal UVC lighting and far UVC lighting?
Okay, so it's fundamentally down to wavelength. Yeah. So germicidal UV is pretty much what we would call 254 nanometer UVC. Yeah. And that wavelength is one of the two principal wavelength that comes out of mercury gas discharge lamps, which is the fundamental traditional way of making UV light. It has two particular wavelengths, and one of them gets absorbed in the glass, so it doesn't make its way out, but the 254 nanometer does. So it comes out of the bulb, and there's a range of different types of bulb that you can have that employ this technology. Some are very long, some are small. You can find them in Canadian Tire. I have one. I bought one a while back myself. The far UVC, it is made at lower intensity in these kind of lamps, so it does exist there. And if you could filter out all of the other wavelengths that you don't want, you could use it, but it's not necessarily the most efficient way. And what the kind of revolution in this kind of field was the use of plasma-based light sources and excimer lamps predominantly. And these excimer lamps, they use particular kind of diatomic molecules that you can excite, just like I talked about earlier with the electrons jumping up to a higher level. And when they relax at particular wavelengths, one of which is to around about 222 nanometers. Now, that's not the only wavelength that comes out. So you have to use a filter, a specific filter, to filter out the components that you don't want. But these new kind of lamps, they allowed greater intensities of this kind of 222 band, and made the process of the filtering less troublesome. So it's really only down to wavelength.
Mm. And the big thing with far UVC is that it's safer
Yep.
than the conventional UVC. Do you want to talk about that? How much
Yeah,
safer
sure.
it is?
Sure. So if it kind of relates to the history of this, actually. So if we went back some amount of years, 10 years or so, maybe a decade, it was recognized, and Brenner's group at Columbia University was one of the pioneering groups in this area. It was recognized that far UVC wavelengths will penetrate less deeply into tissue, which is the fundamental bit that makes UVC light dangerous to us normally. Yeah. So they came along and they figured out if they took this lamp and they took this a particular kind of filter, and they brought it together, they could make systems that could be used to kill pathogens, to kill microbes. Now, the way this kind of works is, talking about fluorescence and talking about electron movements. Yeah, what happens is every time that radiation hits material, the atoms and molecules in that material, their electrons get affected by the energy that's coming in. Yeah, they can get knocked out, they can get promoted to higher orbits wherefrom they relax. Now, UVA light actually penetrates really deeply. Yeah, and this is kind of counterintuitive, because as you go into shorter wavelengths, the frequency goes up and the energy goes up. Normally in life, we think about things like X-rays. X-rays are higher energy photons, and we largely think about them as being damaging. And you go to the hospital and you see the radiation sign on the door, and you know you're not to go in there because it can hurt you if it's not used properly. So this is where it's kind of counterintuitive, in that UVA has lower energy but penetrates tissue more deeply. Thankfully, it doesn't have the energy to cause damage to DNA. UVB does, yeah, which is why people get melanoma. Yeah, UVC does, yeah, it goes less far in, but still hits cells that are living. Far UVC, on the other hand, is so energetic, yeah, it interacts much more readily with atoms and molecules in the dead skin layers that we have, or the tear layer that we have on our eye. And all the energy gets absorbed before it hits anything that's living, anything where we've got DNA that could be hurt. And that's really the fundamental advantage about far UVC light, is that whilst it's got more energy and can cause damage, it can't make it to those parts of us where we could be harmed. And I like to think about interactions a bit like if you went into a bar, yeah, and you're trying to make and it's a busy night, and you come in the door and you're trying to go to the bar so you can buy a drink or a coffee if you don't drink. Yeah, if there's lots of people in your way, you're gonna have lots of interactions before you make it to the bar. Yeah, if there's less people in the way, you get to the bar quicker. And this is fundamentally what's happening with the difference between the different types of light. Yeah, so whilst it's carrying damaging energy, yeah, it has so many more interactions on the way to the bar, the energy gets lost. Yeah, so that's why it's so powerful.
Right. So we get this unique property whereby it can kill germs,
Yep.
but unlike conventional UV light, it won't cause cancers because it doesn't interact with DNA in living cells, and it won't give us cataracts. So
Yep.
we can have a light that shines directly on us, killing the coronavirus in the aerosols, and live happily without the dangers of cancer or cataracts.
Absolutely. And this is really where a huge amount of work has now been done. So prior to the pandemic, there are a number of groups, obviously the Brenner group being one, the Dundee St Andrews group in the UK, group in Japan, I think Kobe University, and some others. They were all already doing work on this. Yeah, so they were looking at, they were exposing skin in mice, for instance, and the eyes on mice, and they were seeing what the effects were. And obviously, since the pandemic, this has taken off massively, with many more groups joining the field, and they all see the same thing. Yeah, you can put very large intensities of far UVC light on the skin and not get any damage, none at all. Yeah, and it's been repeated over and over.
And that's really reassuring that that experimentation has been repeated, and there is a scientific consensus there.
Yep.
So how was far UVC discovered?
So I kind of touched on that a moment ago when
Mm,
I sort of suggested that uh, around about a decade ago, the it was noted that these kind of wavelengths wouldn't be able to penetrate as deeply through cells, yeah, through tissue, and therefore not be able to cause harm. And so bringing together the the technology that had evolved in the lamp space, excimer lamps and the like, along with the right kind of filters, allowed it to be exploited. Clearly, it's always existed
mm,
because it's part of the electromagnetic spectrum.
mm.
It comes out of all UV lamps and almost certainly is produced in the sun and is produced all over. It's just never been able to be exploited because the technology wasn't really there to do it. But once the technology was there, you can see the applications of it, and that's where we find ourselves now.
Okay. So, in what scenarios and environments do you think far UVC would be most effective in the prevention of COVID-19?
Okay, so I went to a conference last week. It was the first conference I've been to in 2 years, and a large number of people started the conference wearing masks. Yeah, uh, and they were trying to be mindful of the fact that we know that COVID is carried in the air, and they would be talking to a lot of people. But they realized that when they went into the reception hall, and people had some canapes and a glass of wine, and they had this big space with hundreds of people and pretty poor airflow. Having a mask on was kind of moot. Yeah,
Mm,
all the mask was doing was acting as a little bit of a filter about what's going in and out. The airflow in the room from the HVAC systems was clearly insufficient to pull the air in and out. If we had had a technology like far UVC illuminating all of that air while we were in there, the concentrations uh, of SARS-CoV-2 or any other airborne pathogen would be being reduced as the far UVC photons get absorbed in the bugs in the air and cause them to be damaged. And if they're damaged, they then don't work properly and they can't infect you. So the spaces where it's very useful is spaces where airflow is very, very bad. Yeah. So when you're outside in the world, you have lots of air around you. The wind blows, other things. There's lots of space. Yeah. You dilute any of the kind of concentrations of virus that people might breathe out. So your risk level goes really far down. Yeah. And that's good. We like that. We know that if you go into a space and you have really good ventilation, it works. Yeah. You can pull a lot of the bugs out of the air. Yeah. By exchanging the air. You could run it through a filter. But the problem with all of those is they need to take the air somewhere else. Yeah. And whenever you can't do that or can't do that very well, you're going to get it to build up. So I rode the Via Rail train from where I live to Ottawa for this conference, and I was pretty uninspired by the ventilation on the train. Yeah, you can't open the windows. The windows are sealed. It wasn't obvious that there was aircon that was working properly. There were a ton of people in there eating and drinking. So that's a terrible environment to have circulation of aerosol in the air. So having far UVC lights in the ceiling of the railroad car would be probably a good idea. Yeah. Similarly, the classroom. Yeah. I have a lot of discussions with colleagues about whether we should have masking still in the schools or not. And I try and make the point that a mask is just a filter. However good the filter is, it's still only a filter. Yeah. So if the filter is 50% efficient, yeah, all that does is double the time before you get the same concentration as you would have got anyway. If there's an infectious concentration in the air, you sit in the room long enough, it doesn't matter that you're wearing a mask. Yeah. Now, there are ways to get that out of the room, but a lot of schools have put those kind of air purifier devices at the front of the classroom. Yeah. And so it pulls the air from the back of the room to the front, past the heads of all the kids. It's kind of a bit of a not well thought through problem here. And it only is when it gets there does it do with the cleaning. So you're actually spreading the stuff around, which you don't necessarily want. If you had them in the ceiling, again, you could kill some of the concentration of the bugs in the air, of all the bugs in the air. Doesn't really matter which. And this has been proven too. Whilst we sort of were the pioneers of the modeling and simulation side of this, that my colleagues and I, a group in the UK, along with Columbia University, has very recently, last month, published a good paper where they have actually done some room-sized chamber experiments, and they've found that far UVC can knock out bacteria in the air down to 2% of the concentration, a stable 2% on a constant release in about 5 minutes. That's equivalent to 184 air changes per hour for that room.
Wow.
And that's using standard UV limits as well. Fantastic performance.
Yes, that's amazing, because I mean the best HVAC system will give air changes of around 6 to 9, I think, from memory, from Professor Jimenez. So that's amazing. So, and again, I think it highlights that you need some form of expertise or some form of regulated setup to help schools assess their environment and work out which technologies to use, I guess, in tandem to provide the best risk reduction methods in terms of removing the coronavirus.
Yeah, for sure. I mean, I'm obviously pro far UVC. I think it's a very good technique. But like so many other things in life, it's not the only solution. And it's not like, oh, you should only use far UVC rather than something else. All measures are needed, like everything in life. Yeah. There are some contexts where it will work better. That experiment that I just spoke about was a very specific setup. Yeah. But make that more complicated by having people moving through the space. You have obstructions so that the airflow is stalled. The room layout is different. Everything then changes. Yeah. So when people say that this technique or the other technique will give this amount of performance, yes, it could, under a certain specific set of circumstances. And this is where implementation is really the key thing. It's understanding how the interplay between aerosol, HVAC or other ventilation, other measures that we have in space, be it illumination, be it masks, be it whatever, how they all work together. Because sometimes they work against each other.
And also, you've highlighted another property whereby, the introduction of far UVC would have wide-ranging properties. For example, if your recent research paper has shown that it's killing bacteria to that degree and will help to prevent other germs that might be floating around, and also possibly other viruses and bacteria that might cause future pandemics. So it's not something that would just help us with this pandemic. It would help us with, it would have far wide-ranging properties.
For sure. I mean, if we think back 2 years, nobody expected COVID to happen or to be what it's been. Yeah. It caught everybody a little bit up by surprise. In the Western world, especially, governments that had pandemic plans that had worked on and published before, they didn't seem to follow them properly. 1 minute they're saying it's not an airborne virus. Next minute it is. By that point, everybody's already moved around. They weren't wearing masks and it's spread everywhere. Yeah. Would we be where we are now had we had some kind of defense in place in January of 2020? And I don't know the answer. maybe we would have been in a different space. But you could envisage that if you had something like far UVC that sits there passively in open spaces, in public indoor spaces, predominantly in transit situations, you would suppress a lot of infections across the board, whatever they are, be they new or old. Yeah. And if we suppress them, yeah, a bit like the masks do, yeah, if we suppress them, less people catch them. If less people catch them, we're able to handle it better and put other mitigations in place. So I think about things like far UVC as not so much something for COVID now, but for COVID 3.0 that comes along later. Yeah. Or some other pandemic that we haven't thought about yet.
Yeah, I think it's really important for 3.0 or future pandemics, whatever they may be. But I think it's also important for COVID, because COVID just has a propensity to cause such a huge amount of chronic disease. When you're looking at long COVID figures, up to 30% of people that catch COVID are going to end up with long COVID if they're unvaccinated. And at best, preliminary research is showing that vaccination will reduce that by 50%, but 15% is still a very high number. And then we're also seeing possible organ damage with people that are even asymptomatic now. So Professor Banerjee in a previous episode talked about research that he'd done to show that. So I think, this is the whole point of this program. We need bits of risk reduction technology, whether it be vaccination, whether it be far UVC, whether it be air filtration and ventilation, all working in tandem to keep us safe and so that we can get back to normal life safely. I think that's what we need.
I think you're right. And I find it kind of bizarre, that Western governments, European governments in other countries spend so much money on things like defense, yeah, which I think is necessary, but we don't seem to do the same thing in defense for health.
Yes.
And this is when we see the economic cost that when we get it wrong, like for COVID, the economic costs of that. If we had done something and invested some money early and been more cautious before and more prepared, I think is the better word, I think things would look very different. So moving forward, for continuing COVID, because it doesn't look like it's going to go anywhere, unfortunately, at least not in the near term, and whatever comes next, I think building in engineered passive solutions is really the best way to bring people back to a normality of life that they want, yeah, whilst not losing the advantages of some of the more visible protective measures that have been used in the past 2 years.
Yes. Yeah. So we could, there still might be instances where we need to use masks,
Yep.
but that would be reduced if we had far UVC technology and air filtration, people were adequately vaccinated, all of that working in tandem. Is that what you mean?
That's exactly what I mean. I mean, having far UVC there for the vast majority of people might mean that people don't have to wear masks frequently. And those people that do are the ones that have more significant concerns. But the people that sit there now and are worried about their neighbor who's maybe not being as cautious as them, they can get some reassurance that far UVC is picking up the slack. Let's put it that way. And I think that will make everybody safer.
Yeah, and I think you actually bring to mind an important point, because if you take like kids under the age of 2, it's really difficult to get them to keep a mask on.
Yep.
And elderly people that suffer from dementia or people with learning difficulties, very difficult to keep masks on them. So if we had far UVC lighting in those environments, it would really reduce their risk and the risk of those around them.
Yes, absolutely. It's a tool that's so useful in many contexts.
Right, okay. You've answered a lot of my questions, which is fantastic. So, one that sprung to mind is what is the speed and distance that far UVC would work? For example, how far would I need to sit from an infected person? Say if we were in a restaurant and I had a friend who was contagious with SARS-CoV-2 and I didn't know it. And we had like a far UVC light shining on us from above, illuminating the restaurant. So how close would I need to be, or far would I need to be from that infected person with the far UVC light shining on us for me not to be infected by their aerosols?
That is a hugely complicated question to ask because there is no one answer. And that's where the reality of how technologies interplay with the real world, exhibit themselves. So right now, most of the lamps are working to the current threshold limit values that exist, and that is 23 millijoules, per centimeter squared of energy in an 8-hour period. So you can pretty much do the math on that and work out that you're just shy of about 3 millijoules per centimeter squared. So that's energy. So we're spreading energy over a small area. And that is what the limit sort of tells us. At those limits, if you're sitting opposite somebody in a restaurant and the airflow isn't in your favor, all far UVC would do is reduce the concentration that you get. So think of it a bit like a mask. Now, if you were closer to the lamp, you would get more intensity. You might go above the guidance level, but then you would kill more quickly. If you were further away, you'd kill less. If you're in a shadow, and the lamp's above you, and you accidentally cause a shadow to be there, the light can't hit it. So it's only as effective as the amount of light it can see. And this is where real world implementations are a problem, because if you think about HVAC systems, they circulate air very commonly. They circulate air around a room. So they might move the air closer to the lamp and then blow it back around again. And then it blows in your face. If it's got less concentration of virus there, that's a good thing for you. But I don't think that anybody can say that you can kill all of the bugs that are coming out of a friend's mouth if you're sitting there at a table at a restaurant. And I don't think we ever can. And that then creates its own question about risk. Now, some companies have considered whether having much higher intensity far UVC sources in between people, almost like a curtain, if you like, could be a much higher power. And because you're not in that illumination field, you would kill more bugs. And I think that could work too. And that would reduce it again a bit more still. But the idea that we can reduce it to zero, I think is highly unlikely. But you could reduce it to sub-threshold infection levels or comparable levels to what you'd get outside, which is pretty much what the experiments in the UK recently found.
So it's a bit like what we've been talking about earlier. We need this, I call it 360-degree risk reduction, pandemic mitigation, and other people have called it kind of a Swiss cheese thing, layered thing. So you need bits of everything. So if you're sitting in that restaurant, you want to know that you want to educate that population to get vaccinated because that reduces your risk.
Absolutely.
You want an air filter or air ventilation, a well-ventilated environment, because that would remove more. You want people to test before they come. if they've, say, that person who I'm sitting next to or other people in the room might have gone to a big football match or an indoor concert, you'd want to encourage them to test themselves before they put themselves back into an indoor environment with others. That would reduce the risk. And then you've got far UVC lighting, which would reduce the risk down further. So it's that whole layered effect of risk reduction that we need to educate the population about, so that they get on board with doing it, so that they can get back to some form of safe, normal life. That's more or less what you're saying, really.
Absolutely. I mean, I think about cars. Yeah, when you drive your car, you wear a seatbelt. So if you do get in a crash, you don't go through the windshield. Yeah. You make sure that your brakes work so that you can stop if someone walks out in front of you, so you don't hit them. Yeah. You make sure that that you can see through the windshield, so you're not driving blind. You don't drink and drive. All of these things all work together to improve the safety for all of us, both the person that's in the car and the person that is on the street. Yeah. And take any of those out of there and you increase risk. So the important thing is to understand how the risks work with each other. The interesting one that you mentioned was far UVC and ventilation. Yeah. So this is a really key part of the equation, is if you get the ventilation profile wrong, you reduce the effectiveness of the far UVC rather than increase it. So I actually think that in areas where airflow can't be removed in a good way quickly, in an amenable way quickly, something like far UVC is a really good thing to put in place. So I have a colleague, she does a huge amount of advocacy for long-term care. And many of the long-term care buildings are kind of old and don't have good ventilation. So if you're thinking about some of those spaces, they're perfect candidates for things like far UVC, because they would just sit there passively, and that air that's circulating naturally through the room would be somewhat sterilized. And that's the kind of thing where we really need to think. But it's like everything. Whenever you install something, if you get some electrical works done, you make sure that the electrician tests the installation before you go and start switching things on, so it's safe. So I think the same is true when you install far UVC. The mistake would be just to run down the store, get a lamp, stick it on the ceiling, and assume it's going to work the way you think it is. But that's the same with everything.
Yeah, that's such an excellent analogy you gave with the car, and excellent examples there with long-term care and where far UVC could be so useful. I think for me, this whole series is important so that the public can be educated and demand the technology, and then we need, government setups really nationally and internationally, where people are trained. We have trained engineers that can go around and educate people on how to facilitate these setups correctly. I think there needs to be a whole organizational network to put this technology in place, in my opinion.
Yeah, I could say it now. If you go back, some many decades, you find much more common reference to something called public health engineering. Yeah. And that doesn't seem to be something that we spend as much time thinking about these days. We think about public health and we think about engineering, but those two things intersecting, I think, is where the next 20 years needs to be.
It needs to happen now, in my opinion. I mean,
yeah, I'm not saying that we do it in 20 years. What I'm saying is, it's something that we should be doing.
Yeah.
And, the field needs to establish itself so that we understand that, okay, you can reduce infection by changing the way people walk. Yeah. So rather than have them snake next to each other, so they're cross-pathing all the time, make them go around a slightly different way. And that then changes the dynamics of the situation. And the same is true with far UVC. you know.
Yeah, I think Professor you, Kirk, and Jose Jimenez have really pointed out that, we need scientists and engineers to be more involved with public health, because how the virus and other pathogens such as bacteria act in the environment is really your domain. The physics of the environment and how things like aerosols, light, etc. interacts is your expertise. And as medics, how the bacteria and viruses work within our body is our expertise. So the medics have done fantastic jobs, but
Yep,
it's only half the solution to
for
us
sure.
living safely. I think you've really highlighted that today.
Yeah, for sure.
Okay, so we're running out of time, and there's a couple of important questions I wanted to ask.
Yeah.
So currently, far UVC bulbs are expensive, partly because there isn't the demand due to the lack of knowledge about the technology, and partly because there isn't an LED equivalent. When do you foresee an LED version of the bulb being made available so that so that they can be mass produced for, say, our homes, for example?
So first thing is, if we roll back a year or two, the lamps were significantly more expensive than they are now. So there are a lot more vendors on the market, a lot more people playing in this game. I think we're still not getting the message out well enough as to the fact that they could be useful. Yeah, and I think in some people's minds they've already moved on. Yeah, and so they're not investing the same kind of considerations they were before. They feel they've got their solutions, and that's that. And I think that's flawed. Uh, but I think we're much more in a zone now where we're in the comparable to water sterilization cost range. So that is still expensive relative to your standard kind of energy efficient light bulb that you stick into your fitting at home. And I'd say we're still some ways away from that. The LED thing is interesting. It's easier to make LEDs for longer wavelengths. Yeah. And this is fundamentally where it becomes a technology problem. And it might well be that you can make far UVC LEDs, and there are people that do work on this already. But their efficiency and their intensity, their output, isn't necessarily very high. So I think if you really wanted to speed things up, you want somebody with sufficient money to scale the technology that already exists so that it's cheaper and can be mass produced more quickly. And whilst there are big companies involved, what you need is you need an Elon Musk or somebody like that to come out and punt up a lot of money to make it so, and then it will take off. Yeah, and then the market will do the rest, because none of this stuff is very hard to do. It's just that it will scale to demand. Yeah, so demand has increased, competitors exist, prices come down already. Price will continue to come down. If we went back and thought about how much cell phones cost when they first come out, and now think about that you can buy them and they're almost disposable. Yeah, that cost can really change quite rapidly. So I think it's less about waiting for the LEDs, although the LEDs is a kind of neat solution, and they will come in time. I think it's more about getting the message out there to the people that can influence purchasing power, and then the market will do the rest.
That's an excellent answer, Kirk. Thank you for that. You talked in the beginning about how the research you and your team did enhanced the research that Professor Brenner did in Columbia. Could you talk a little bit about that? What you've done?
Yeah, sure. So in 2018 and then in 2020, the group in Columbia made some experiments with a benchtop chamber. This is before they managed to get access to the one in the UK, which I spoke about earlier. And this benchtop chamber had sort of an inlet and an outlet, and blew some some air through it that had been seeded with coronavirus. It was a different human coronavirus, but it's very much representative. And the way this system was set up, it had a kind of window and a lamp on the outside and some structures, and various things were happening. And they made a rough approximation about, this is the size of the chamber, this is the speed of the air. And then when they looked at their results at the end for the amount of illumination and the reduction in the infectiousness of the virus that was in the air, so how many virions had been killed effectively, they made an estimation of what the susceptibility of the coronavirus was to far UVC. But it neglected a lot of things, yeah, because when you blow through a tube, you get drag at the sides. So that means it slows things down, yeah. So if any virus that's near the edges is staying in the light longer, and actually the virus that's in the middle, being blown through the middle, moves the quickest, so stays in the light comparatively less time. And then there's shielding effects and distance effects that they hadn't really accounted for. So we were able to help them with that, and actually showed that their susceptibility was about half of what it really was. Yeah. And that was what that was the key finding. And we've had a couple of papers out with them on that topic specifically. So it shows that actually for coronavirus, human coronaviruses, far UVC is exceptionally useful. And coronavirus is very sensitive. Now, you'll remember I talked about the fact that the far UVC couldn't make it through the skin. Yeah, because these viruses and these other pathogens float around in the air, they're so small, those far UVC photons, light rays, they're able to get absorbed by them. And fundamentally, that's what this thing does. And the susceptibility is really a measure of how well far UVC or any other light, how good it is at killing that particular pathogen for a particular energy, a particular amount of time or area.
Great. We're practically out of time. And I just want to thank you, Kirk, for your contributions today. I really wanted to inform the audience of this amazing technology that has the scope to change all our lives and help us to live safely with this coronavirus. And you have really facilitated that. Thanks to you and your colleagues for all the marvelous work that you're doing to keep us safe.
That's no problem. You're welcome. I mean, I think there are lots of people across the world doing lots of great stuff. And we actually talk to each other, which is a good thing. Yeah, because that communication is really a key thing. Sharing the results will mean that we're quicker to respond to threats.
Very much. I think the most successful aspects of the pandemic has been the collaboration and the openness with science that's been facilitated.
Thanks for listening to this week's episode of COVID-19 The Answers. If you enjoyed the episode, please subscribe, rate and review, and do visit our website kajalamedical.com/COVID-19 The Answers.